Okay, this video looks at B1, which is Newton's 3 laws of motion. So we understand a little bit about force already, and now we're going to work through each of the 3 laws of motion. Before we get into Newton's first law, let's just recap what we understand by inertia. Inertia is the resistance of any object to change motion, whether that object is stationary or whether that object is already in motion. And hopefully from 7.1, you understand that inertia is directly proportional to an object's mass. So an object which has a large mass has a higher inertia, and an object which has a small mass has a smaller inertial value. And therefore, this bigger object, I say bigger as in terms of mass rather than size, because it isn't just the size or the volume of the object, it's the mass specifically. This larger massed object has a greater resistance to change motion than a smaller massed object. So inertia is proportional to mass. To change the motion of objects which have a bigger mass, what we will need is a bigger force. So it makes sense that this poor chap trying to push this 400 kilogram mass will have to exert a much larger force on it to change its motion, whether this object is still and it's trying to start motion, or whether it's already rolling and he's trying to accelerate it and speed up the motion. In either of those examples, he will have to apply a much larger mass than this other 40 kilo mass. So some basics just to recap. We certainly talked about the first 3 bullet points. We probably did talk a little bit about, well, how much force do you need to change motion or to overcome inertia. So you might be aware of that already. Obviously, we have loads of examples of this. This is quite a bizarre chap here lifting a huge, unimaginable amount of weight. So 500 kilograms. His muscular force against gravity to lift that weight must be absolutely colossal. You're going to think of your own examples to obviously relate to these 3 Newton's laws. Why did I talk about that? Because Newton's first law is the law of inertia. So it kind of revisits what we know already, but has a slightly different focus than just inertia being related to mass. It's more than that. It's to do with the forces required to change motion, to overcome inertia. So an object at rest will remain at rest. This ball will stay sat on the ground there. It has a resistance to change its motion. It's quite happy being still, unless an external force, an unbalanced force, is acting on it. So the force that's applied by this foot acts as an external unbalanced force, which, if it's powerful enough, will change the motion of that ball that was still and create, a shot. It will accelerate away. An object in motion will continue. So that's one example. It will stay still unless we have an external unbalanced force changing its stationary motion to making it move. The second point is this ball, once it's in motion, will travel at a constant speed and velocity in a given direction unless there's an unbalanced external force acting on it. Now, 2 options. One, it's a goal. It hits the net. The net acts as a force, so the net will apply a force to the ball in that direction, right to left, and make the forces, so force going that way would be bigger, because this is fixed, of course, it's attached to the post, and therefore creates an unbalanced force in the right to left direction, and the ball will decelerate. Okay, the ball will slow down and stop traveling in that direction. It changes direction as well, incidentally. The other thing that would be true of the ball, if there was no goal, let's say this was out in the pitch, the ball just doesn't constantly fly through the air. We know that ultimately it has this parabola and it will come down to the ground. That is because there's also another force acting upon the ball, and that would be gravitational force acting down through the centre of mass of the ball. And the longer this ball is in the air, the more gravity is acting on it, and the more gravity is accelerating the ball down, because it acts as an external unbalanced force. So in all this example, first example, goal example and air ball example, motion changes because inertia has been overcome by an unbalanced external force acting upon the ball. So, some facts. A body will maintain a state of rest, still, or constant velocity flying through the air, unless acted on by an external force that changes its state of motion. We've given examples of that. The resistance of a body to change its linear motion, whether stationary, so it's just saying inertia has a resistance to change motion. We need forces to change motion. And this is called the inertial principle. So again, in class we may have used these sorts of examples already when we talked about inertia and momentum. But essentially, if this athlete was running down the pitch, he has quite a large mass. He has therefore quite high inertia, a resistance to change motion. So for him, running along, to dodge, to change direction, to accelerate, he's got to apply quite a lot of muscular force to accelerate himself, either in a different direction or to speed up. That's hard work for him. Equally, for this defender to overcome this attacker's inertia, because he's got quite a big mass, this would be quite a tough task. He's got to apply a bigger force than his inertia if he's going to decelerate him or stop him somehow. So remember, mass is linked to inertia. To change motion of any object, whether it's the attacker trying to change his own motion or the defender trying to change the attacker's motion, we need forces. And the bigger the inertia, the more force we need to change motion. Conversely, this athlete over here, so it tends to be the wingers in rugby, tend to be a little bit more slight, less big, bulky, smaller mass. Him accelerating, for him to speed up, he'd have to generate smaller forces to accelerate himself because he has got a lower inertia, lower mass, easier to change direction. These guys tend to be a little bit more agile than these guys because it's easier for them to apply forces to change direction, to accelerate, to decelerate. Similarly, though, to tackle him, if you ignore the fact he might be running fast in this picture, to tackle him and stop him might be easier for a defender because he is a smaller mass and a smaller inertia. So for a defender to change his motion might be a little bit easier. And you could argue these sort of athletes, the forwards in rugby, might try to increase inertia by bulking up, by getting big. I'm not saying it's all lean mass, a lot of it will be, but there might be some body fat there too. These guys try to get lean and strong, but lean, so that they can be faster. So they are manipulating perhaps their mass for performance advantage. So perhaps have a think about who else might do this to make it easier on themselves so that they either don't have to generate as big a force to move themselves, or other people might have to generate bigger forces to change motion on them. So have a little think about where we manipulate inertia, manipulate our mass for some kind of performance advantage. So who might get an advantage by reducing their inertia of themselves or their equipment, I should say? You might look at endurance athletes. They tend to be quite lean. They have muscle, so they have muscle mass, but they try to reduce their body fat, their fat mass, as much as possible, because fat mass is just extra weight, extra mass to carry around. So they will have to generate bigger forces to move themselves if they are heavier. So the lighter they can be, the less force they need to propel themselves, or if they can generate big forces, they will be faster. They will accelerate more. So it's an advantage to be lean as an endurance athlete. Similarly, clothing. So if you think about elite cycling, competitive bikes, they are super light. You can lift them up with one finger because a lot of money is spent on the frame, every bit of technology on that bike, making it as light as possible. Even the clothing we wear. So a lot of footwear nowadays is designed to be as light as possible. Functional, yes, but as light as possible, so that it is less effort, less force is required by the athletes to propel themselves. So this is an example of how we might reduce inertia, reduce mass, so that forces applied either can be less or can be more for acceleration. Examples where we might increase inertia or increase mass for some kind of performance advantage. Well, I think obvious ones are when we train, we choose to lift objects of higher mass to make our muscles learn and adapt to apply bigger forces, and we therefore physiologically adapt and become stronger. So this is all about trying to make our bodies and our muscles adapt to generate bigger forces. Even things like tennis rackets have different weightings, different mass. If they're lighter, they're easier to manipulate and hold and swing. If they're heavier, they're perhaps more challenging, but you might get more power in the end. And the same would apply to drivers versus something like a putter. So the drivers tend to have this bulbous club head, which has more mass there, and therefore the athlete needs to generate bigger forces to swing it, but when they can do that, they will accelerate the golf ball much more, and the ball, this is the one you hit off the tee, the ball tends to go much further when you do. Okay, so that was Newton's first law, the law of inertia. Objects require force to change inertia. The bigger the inertia, the bigger force is required to overcome it and change motion. So, we're moving on to second law now. This server could apply a force to the ball and send the ball in all sorts of directions and with different amounts of force. Okay, so different directions and different amounts of force and in different accelerations. If you apply a bigger force, the ball will accelerate and go away much quicker than if you apply a smaller force. So let's have a look at those sorts of variables, the amount of force you apply affecting acceleration, how rapidly this object accelerates. So a small force will generate a small acceleration. A same size small force, but if you have an object which is half the mass or a lower mass, a lower inertia, you will get a bigger acceleration. So the same force is being applied to these two cars. This one has a big mass and therefore big inertia, resistance to change motion. This one has a small mass, a small resistance to change motion. This one will accelerate a little bit. This one will accelerate a lot more. Hopefully that makes sense. So the acceleration is proportional to the mass. If you've got a large mass, a large inertia, even larger, and you apply the same force, obviously the acceleration is halved again. So you can see that the force happens to be consistent here, but the mass of the object varies, and therefore proportionally the amount of acceleration varies. So that's one aspect of Newton's second law, that acceleration is connected and proportional to the mass of the object. But it's also linked to the force. So just to use this same example, if we wanted all three cars to accelerate at the same rate, hopefully you can figure out you'd need to apply a massive force to this car to overcome that big inertia. You'd have to apply the smallest force to this car to overcome a small inertia, and you'd have to apply a medium-sized force to this car to overcome the medium mass and the medium inertia, so that all three accelerated at the same rate. So just to revisit a concept that came out in the introduction video, balanced or unbalanced forces. If forces are balanced, they're equal and opposite, then we know that objects will stay still, or objects will stay in motion at a constant velocity. So there's no change in velocity when forces are balanced. But if we have unbalanced forces, there's a force in one direction that's bigger than in the other direction, we have a net force. However big the difference is the number of that unbalanced force in whichever direction. So this law, second law of motion, is the law of acceleration. And what we will understand is that acceleration is proportional to the net force. So going back to our scrum example, if there was 5 newtons force in one direction, 10 newtons force in the other direction, the team pushing in the 10 newtons force would accelerate in that direction because the net force is 5. There's 5 more, a greater force of 5 in that direction. So there will be a change in motion and there will be an acceleration in that direction. So acceleration is proportional to the net force, but it's inversely proportional to the object's mass. And that should have come out in the car example. Let me just go back to that. Big force, big car, small acceleration. Tiny car, biggest acceleration. So these are proportional, inversely proportional, I should say. The mass or the inertia is inversely proportional to how much acceleration is generated, given that the force is the same. Of course, force might vary, but if the force applied is the same, the acceleration is inversely proportional to the mass of the object and therefore the inertia of the object. So, as I said, this is Newton's second law of motion, the law of acceleration. It has a little bit more to it, so there are a few aspects to connect here. The law examines the relationship between mass, force, and acceleration. The examples I've talked about already integrate those three concepts. Definition-wise, a force applied to a body causes acceleration of that body of a size that's proportional to the force, i.e. the bigger the force applied, the acceleration will be proportional. Okay, so big force, big acceleration, small force, small acceleration. The acceleration will be in the direction the force is applied. So if this hockey player applies a force in that direction, the acceleration will be in that direction. If they apply a small force in this direction, the ball will accelerate a little bit at a low rate in that direction. However, we also need to understand that acceleration is inversely proportional to the mass of the object. So if you apply a force to a small massed object, it will accelerate a lot. If you apply the same force to a large mass object, it will accelerate less. And that came out with our car example. Please note that acceleration is a vector. So we should know this from 7.1 anyway, and it's measured in meters per second squared. So we should technically account for direction. You've got to have unbalanced net forces for acceleration to occur, because without an unbalanced net force, the net force is 0 and motion does not change. And of course, acceleration is in the direction of the force being applied. So some little examples for you. We've got athletes here who I am saying are of the same mass. Pick any two athletes, they are the same mass. So how would it be that one accelerates from the blocks and gets to 10 meters first? Hopefully you know that's an obvious answer. Essentially, if they apply a bigger force back in the blocks will accelerate them forward faster. So the bigger force they apply pushing backwards, the bigger the acceleration forwards to get them to 10 meter mark first. Another example, we've got two athletes who are clearly of different mass, but if they applied the same amount of force back into the starting blocks, who would accelerate the most and why? Hopefully you know that because the law of acceleration says acceleration is inversely proportional to mass, if you apply the same force, this athlete has a small mass, small inertia, they would accelerate more rapidly than this athlete who has a larger mass, larger inertia, given the same forces applied. But what would this athlete have to do? Let's say we want them to accelerate out of the blocks at the same rate. What would this athlete have to do to achieve that? Because they're a bigger mass, they would have to generate much bigger force to achieve the same acceleration than the smaller massed athlete. So how do we calculate acceleration incorporating force and mass? We've done some versions of acceleration in 7.1. The equation here is slightly different. So first of all, hopefully you understand and appreciate already that in most cases mass is a constant factor, it's a constant value, whether it's athletes or equipment. And what we tend to want to find out in sports science, in biomechanics, is either what force would be required or is being generated, or if we apply a certain force to a certain object with a certain mass, what would be the acceleration? So we tend to want to work out force and or acceleration. But this is the equation that we're going to use, and actually we can rearrange that depending on which of those factors we want to calculate. So if we've got mass and acceleration values, we can times those together and figure out what force is being applied. If we've got force and mass, we can divide them and figure out what the acceleration is. And if we had force and acceleration, which we don't tend to, we could calculate what the mass of an object is. So we're likely to use these two to either calculate the force required or the force being used or what an acceleration is. So let's just have a look at one of each of those as an example. In class we'll do more, but you obviously will need to find your own sport-specific examples. These are not sport-specific, they're just using numbers to show the mass. You guys need to give your examples in a sporting context. So if we had an object which had a mass of 30 kilograms, which accelerated at 5 meters per second, we wanted to calculate the force, we would use this version of the equation. What is force? It's mass times acceleration. Essentially times those two together, force is 150 newtons. So if you applied 150 newtons to an object with a mass of 30 kilograms, it would accelerate at 5 meters per second squared. What if we had an object that we wanted to find out the acceleration of? So the object's mass is 30, we apply a force of 14 newtons to it. How would we calculate that? So we'd use this other equation over here, of course. We'd use the acceleration is force divided by mass, put those numbers into the equation, and we get an acceleration of 0.47 meters per second squared. So pretty simple. Once you figure out what numbers have I got, what equation do I need to use, and then you just slot the numbers in. But obviously yours is going to be in a sporting example context. And you're going to use a mixture of athlete examples and object examples. I'm going to very briefly add a little bit of content in. Now this is, I would describe it as icing content. So this is stuff that, is a little bit above and beyond what you must know. If you can grasp this and include it, fantastic. This introduces another term. So we know what momentum is. It's how much motion an object has based on the object's mass and its velocity. So a cricket ball that's been struck will come to the fielder at generally high momentum. The mass is smallish, lowish, but the velocity is probably quite high. The term that we're going to introduce is called impulse, and I'll explain that in a moment. Now you might know from school, if you played rounders or softball or cricket, if you got this ball that's hurtling towards you, if you hold your hands out and you just hold them still and the ball whacks your hands, it's pretty unpleasant because you've got this huge force hitting your hands in a very quick, instantaneous time. So the impact is quite high. That whole momentum whacks your hands and hurts. What you're probably taught to do is to cushion the ball. So you kind of meet the ball, and as the ball arrives, you move in the direction of the ball to cushion the ball. And what you're doing is dissipating that impact, that force, over a longer time. Rather than it being all hitting you in instantaneously there, the force is being applied to you over a longer period of time, meaning that the force on your hand will be much smaller. And that's basically using impulse. Impulse is force times time. So the force applied on your hand over a longer time is better than, a smaller force being applied to your hand over a longer time is better than the whole force being applied to your hand in a very, very short time. So that's obviously summarised in the box up here, basically, what I've just gone through. This can also be applied to baseball. So in baseball, the batter can do what we call a bunt. And that means the ball comes, they will almost like block or tap the ball. So that's a very quick contact with the ball and very low force and low momentum. And the ball will just drop down here. But the other thing that you are coached to do if you want to hit a home run is you have this huge swing and you have this huge follow through, and that follow through in particular, a bit like this could also be tennis perhaps, a volley versus a drive, whereby you have this follow through to try to increase the time that the bat is in contact with the ball. So not only have you got a high force, you've got this high contact time, and that has a really high impulse. So this has a really low impulse, low contact time, low force. The ball will go away with low motion, just near the batter. This one has high time in contact with the bat, high force applied during that time, which is high impulse, force times time, and therefore huge momentum. The ball will accelerate rapidly, high motion. So just to summarize, to change an object's momentum, we need forces that are unbalanced to accelerate the object away. We can achieve this by small force for a longer period of time or a large force for a short period of time. So those two factors are variable. This example over here shows that. If you kick a ball for a short time, 0 time, it will accelerate. If you kick a ball same force but twice the length of time, it will accelerate. It will have twice as much momentum. So force times time is momentum. Force times time is mass of the ball remains constant, change in velocity, acceleration. Force times time, which is small, is a small acceleration, a low momentum. Force times time, which is bigger, a bigger, twice the size, momentum. Velocity is increased, is accelerating. If the time the ball was struck happened to be the same but the force was doubled, it would have the same impact. It doesn't matter which variable changes, or both, it has an impact on momentum. So impulse is the length of time a force is applied to an object or body, and it relates to its change in motion, its change in momentum. And that's the equation. Impulse is force times time, and that determines any change in motion, mass times, mass and velocity. Now we represent impulse by a force time graph. So this shows from the start of time to the end of time, from no force, applying a force, applying less force to the end of that time period. And the area underneath represents impulse. Obviously the bigger area, the more impulse, the bigger force. So you can have a low force over time, you can have a big force over a short time, it varies. But graphs, this is called a force time graph. It represents impulse. This might show it perhaps a bit more. So this looks at horizontal forces, friction forces. So you can see the arrow here in the propulsion phase at the start of a sprint. The athlete's pushing backwards and the friction force is propelling them forwards. And you might imagine this to be a huge force, hence the big space under the force time graph during that acceleration phase. As the athlete starts to become more upright, maybe 20 meters, the amount of friction force is smaller because they're not pushing backwards and forwards as much. They're becoming a bit more vertical. So the area under this graph here is a bit smaller, and you can see also that by the arrows. By the time they're in the middle of the force and they're upright, there are no major net forces. So this was a big acceleration. This was a moderate acceleration. By the time they're in the sort of 50, 60, 70 meters of 100 meter, their velocity is probably constant at their peak velocity. And you can see the forces are equal. So there's no net force. Whatever force is applying backwards is applying. So, air resistance going backwards is equal to the friction force going forwards. There's no acceleration, there's no change in velocity. And then near the end of the race, maybe if they're getting tired or after the finish line, they're slowing down, they are perhaps applying more force forwards with their feet, so the friction force is coming backwards and almost braking them, decelerating them. So now we've got a bigger negative force. So there's a small forward force and a bigger negative force. So they're decelerating. So just one quick example to show impulse calculations, force time variations. A cricket ball is struck and has an impulse of 4.8 Newton seconds. So force is in Newtons, time is in seconds, of course. We could achieve that by a force of 48 Newtons over a time of 1 second. So really quick hit, large force, 48 Newtons, for a short time, just 1 second, and that would be the sum. However, we could also achieve that by applying a smaller force and having a really big follow-through. So the first one could be more a defensive shot where you block the ball. The second one could be a smaller force over a longer time, a follow-through, so applied over 2.4 seconds. And actually what we get is the same impulse, so a small force over a long time. So impulse is force times time. So obviously lots of different sports. You know, we have a big, long bowling swing to have greater time. Javelin, shot put, we all try to maximize the amount of time that we can apply a force onto the ball with. Volley versus drive in tennis, easy examples. If you're going to include this, think of some nice simple examples. So just to summarize, how can we change momentum? We can change velocity, we can change the force, we can change the time we apply the force in. We can slow down moving objects over a longer period of time, like the cricket catch. Obviously, we could change the mass of the object if it's a training aid, but we can't change our own mass. Okay, Newton's third law, final law, is the law of action and reaction. So the swimmer applies a force to the wall, that's an action force, and the wall will apply an equal and opposite reaction force back on them, which is what accelerates them away. The ball here will remain constant unless there's an unbalanced force affecting it. So the kicker applies a large force to the ball, and the ball will apply an equal and opposite force back on his foot. If these skateboarders are of equal mass and they apply the same force to each other, then they will accelerate in the opposite direction at the same rate. Some slightly different examples. You know, a force is applied by the gun internally in the mechanisms when it's shot, and then there's an equal and opposite force backwards that's like the recoil of the gun. If this was clay pigeon shooting, and you've got the shotgun type, gun, which has probably a bigger force, then there would be a bigger force generated to propel the bullet, object, whatever it is that goes out of a clay pigeon gun, and there would be a bigger force, reaction force, back on the shoulder of the athlete. The air, again, not really a sports example, but it gets the point. Air shooting out of a balloon is equal to the acceleration, the reaction force that accelerates the balloon when it flies away. So the principle of this law compared to law 2 perhaps is quite straightforward. Every force applied has an equal and opposite direction reaction force. So when a body exerts a force on a second body, the second body exerts a reaction force equal in magnitude and opposite in direction on the first body. So these are always in pairs. So the athlete will push on the ground and the ground will push back on the athlete to propel them forward. The ball is struck, the ball will strike the foot. You push on a basketball, the ball pushes back on your hand. Hopefully pretty straightforward in terms of Newton's laws. This slide, I'll finish on this slide, just as quite a nice summary of the 3 Newton's laws of motion. I said I'd finish on the other slide, but this is the spec content for this video.